Hello guys, Fadi here. Today we talk about a question I got that is why can't the verifier change the input of the Garbo circuit to obtain a fake proof and force the Garbo circuit to output a false output and therefore being able to block the operator. Let's make a little bit of context. You know that BitVM has a transaction graph. Let's assume there is one single operator. We have the first transaction here, input output, and we have that Alice puts an amount A of Bitcoin and the end of an signer committee is the output and obtain this amount. This is the deposit transaction. This is the first transaction that is published on chain. After that, we have the withdraw transaction that has as input the n of n with amount A, and the output is the operator public key operator that has A. All right, this is the withdraw transaction. It doesn't have only one input, it also have another input, which is a connector that has amount basically zero. It's dust. Okay, and this is the withdraw. Now this is the operator. Let's assume there is only one operator in our system, and now I will put an asterisk here because this transaction is not published yet. Now, where does the connector come from? Well, there is an assert transaction. And this transaction has one input and one output. The output is the connector itself, right? And the input is the data of the proof. It's the proof itself. So what you want here is basically the proof that the operator creates when he fronts money to the user. And the connector goes here. And this is a transaction that is not published on chain, right? So it has a connector, but the connector can also be used for the dispute transaction that has inputs and outputs. It has a connector, and then it has just an OP return here. And the goal of this dispute transaction is just to spend this connector, so that if the connector is spent, it cannot be spent in the withdraw transaction. If we have this, then we cannot have this, right? If we have this, we cannot have this. And the goal is just to spend the connector so that the withdraw transaction cannot be spent anymore. And so in practice, the question is, well, so the verifier can do a denial of service here. It basically, when the assert transaction is posted, and therefore there is no asterisk here, the verifier can, let's call it the denial of service algorithm protocol, okay? The denial of service protocol basically says, well, verifier takes pi, right? It takes the proof. The verifier modifies pi. Verifier modifies pi, obtain pi prime, right? Puts pi prime in Garbo circuit. Verifier obtains false from the garbled circuit, verifier spends connector, right? And the big assumption here, if you think about it, is that you can modify pi to have pi prime. This is the big assumption here. My claim here is that this is not possible. To see why that is not possible, we need to understand how garbled circuits actually work. A garbled circuit, let's say that we have a XOR gate here. This is a circuit, a very simple circuit. It takes one input and it gives you one output, right? And it has a truth table, right? So the truth table of the XOR, is that input 1, input 2, output. It works like this: 0, 0 gives you 0, 0, 1 gives you 1, 1, 0 gives you 1, 0, 1, 1 gives you 0. Okay, this is the XOR table. When you have a garbled circuit, instead of having 0 and 1 as output, you have some kind of encryption. 0, 1 as input, you have an encryption of those values with one key for each input. And the output is again another encrypted thing, right? So you may say, well, let's put things this way. We have the garbled version, so we have garbled XOR. It has key, so input 1, input 2, and output. What has here? So instead of 0 here, you have the encryption, if you want, encoding, if you want, of 0. And here you have the encoding of 0. Here you have the encoding of 1. And here you have the encoding of 1. Okay, I say key because it's key. And since we are talking about input 1, we put a 1 up. And then the second key is 0, 1, 0, 1, right? We are copying the same order: 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1. And if you look at this, 0, 0, 1, 1, 0, 1, 0, 1. What's happening here? We have the encryption using key 1, 0 and key 2, 0 of the number 0, right? Because if you remember, we have 0, 1, 1, 0, okay? And so you have 0, 1, 1, 0. And then here in the second spot, you have the encryption with key 0, 1 and key 2, 1. And here you have 1, 1, key 0, 2. And here you have key 1, 1, key 1, 2. This is a simplified version, but it's enough for us. Because what's happening here is that for this simple circuit here, which is, it has the same topology of the same structure of the garbled version, instead of giving this drawing here in practice, if you have to give you a circuit, I'm giving you this, the set of the tables that give us the circuit, right? I won't give you a drawing, I will give you a table. This is why we talk about the table. Tables are transferred. But since we're talking about garble circuits, I'm not giving you this table here. I am giving you this table here. And this is a table for the XOR. Now, if I give you this table here, right? And then you will be able to get all the data, right? So in practice, I do not give you the whole table. I give you only the output table. So you end up having this thing here. Let's see if I can do this. You are given this, right? And since we are talking about proof, what we are giving you, this is done off chain. And also, let's say that as a proof, I'm giving you the proof, the encoded proof. And in our case, the encoded proof may be something like K01, K12, okay? I give you those two keys. You put that into the table I gave you, right here. And so the only thing that you can open meaningfully is the encryption of K1 and K2 of 1, and therefore obtaining 1. Now you say, well, you want to remember that this is our proof pi, because our proof pi, it may be very complex, it may have many numbers, many encryptions, but in practice they are in this form. Okay, so if we have a very simple circuit, we have a very simple circuit with one gate, which is the XOR gate, which has been garbled here. You get this one here. And so in practice, the question is, okay, you have pi and you want to have f of pi, which is a modification of it that gives you 1 pi prime. So I can have another number. I want to obtain, so this is such that given the output table, GXOR of pi prime gives you 0, right? Because we obtained 1 and we want 0. And yes, I can tell you in theory it's possible. In practice, you need to find k. If you want a 0, you have k01. If you want to have a 0, you have this one. If you want to have a 0, and therefore you have this one, right? If you want to have a 0, you need this one, right? So you need key 02. But the problem is that key 02 is completely different from key 1, 2, right? And there is no way you can derive K02, I'm sorry, K12 from K02. And this is a big, I mean, it's not an assumption, it's something that you can have by construction, right? And so this is it, right? So if the question is, remember where we started, we said, well, I have pi and I want to have pi prime so that I can do denial of service and spend con instead of letting the operator works. And what I did was, well, this is not possible. And why it's not possible? Well, it is not possible because if you look at how the actual garble circuit actually works, it works like this, and the proof pi would be this. And for this reason, since you cannot have another k from the first k, you cannot do this. This is impossible because of this. Hope it's clear.